So welcome to this webinar on the master programs in physics at Stockholm University. My name is Christophe Clément. I am professor in physics, teacher on the program, and one of our program coordinators. So we offer several degrees, and today I will give you more information about the master degree in computational physics, the master degree in theoretical physics, and the master degree in physics. The master degree in physics is further subdivided into 4 study paths. The first path, atomic, molecular, and optical physics. The second path, particles and cosmos. Then we have quantum light and matter. And then finally, we have general physics for students who have not yet decided their specialization. So what are the goals of the programs? The first element is to provide foundations and tools which can be theoretical, mathematical, and computational. The second element is a strong and broad knowledge base. So that means that we encourage the students to sample among a variety of subjects. The third element is to provide a specialization which will give added value to your CV towards a specific class of employers. The final part of the program is to provide research and professional practice. This is done in form of a master thesis project, which can be carried out either in a research group or in a company. So what is special about our master programs? Well, the strong connection with researchers, since all teachers are active researchers. We offer the possibility of up to 1-year R&D projects embedded into one of our research groups. We have a very strong and international research environment, and we are working in connection with national and international research facilities. Finally, I want to mention that we have very strong research seminar series in all areas which are open to students of all levels. So our researchers and teachers come from 7 research divisions, which are listed here. And you can have more information about our research on our website. In all these areas of research, we are involved in national and international research projects. And we have access to the national and international facilities and the corresponding science data. So for you, as a master student doing your master thesis project, you will be able to join one of these national or international projects and use the data for your master thesis. Finally, one thing I particularly appreciate is that in all these areas, we are collaborating with other world-leading research institutions, which make it a very intense and live working environment. So here I show you a patchwork of experiments and projects we are working on. And I don't have time to name them all. I will just highlight a few of them, such as the IceCube Neutrino Telescope located at the South Pole, or the Xenon 1-ton experiment located under Italian mountains and looking for dark matter particles. And we are also working on several experiments at CERN. And we also have experiments here locally in the house, such as the Desiree National Facility or our Quantum Information and Quantum Optics Lab. So I would like now to give more details on the 3 different programs, and I will start by computational physics. This program is made up of blocks of 6 mandatory courses designed to provide strong foundations in computational physics. This block is then further complemented by at least 7.5 credits to be taken among the list of optional courses listed here. And this will be finally complemented by additional credits to be taken among any of our courses. Computational physics is strongly related to the industry, and for this reason, the master thesis projects are most often carried out in a company. So I will now give the word to Professor Eva Lindroth, who is coordinator of the Computational Physics program. Eva will discuss the program with one of our former students and also how it is to move to the industry.
So welcome. Today I'm here with Marcus Tollett, who rather recently graduated from the Computational Physics master program at Stockholm University. Nowadays, Marcus is working at Ericsson, the telecom company. So perhaps you can tell us a little bit about what you're doing, what your title is, and so on.
Yeah, hi everybody, Marcus here. As Eva said, I'm working at Ericsson. My official or fancy title is Integration Engineer. What that means is that I'm working closely with customers, helping them with installing complicated software, maintaining said software. I am also working in general as a consultant towards the customer, helping them with any questions they have towards our products. I am also teaching courses to our customers regarding our products, etc. Yeah, that's briefly what I do.
Okay, interesting. So how come you started at Ericsson from the beginning?
So I have two ins, you could say, with Ericsson. To begin with, during my final year of my master's, I applied for an internship at Ericsson. They have an internship called Young Professionals, which is catered towards almost graduated students or recently graduated students. It is actually through this program in which I am working as an integration engineer as I am doing right now. However, I also utilized that same internship to get a master thesis project at Ericsson. And I got to work within their research and development group, specifically their quantum information group. So I got to do some very, very basic machine learning on an actual quantum computer, which is very, very interesting and fun. Yeah.
Okay, we can perhaps take it from the beginning. So first you had a bachelor degree in physics, and then you chose to join the Computational Physics master program. So perhaps you can tell us why you did that. What was your motivation?
That's correct. So I have always been, a little bit in between. Do I want to study physics or computer science? And when choosing my master's, I thought that computational physics is the perfect marriage, perfect mix of physics and programming / computer science. So in my view, this was the best way to get best of both worlds, so to say. And I think the competences that you get from this master program is very broadly applied, both within the academics and industrial world, so to say.
So was it something you especially appreciated during the master studies?
Yeah, I think my favorite type of courses or challenges was when I was presented with a problem and told, solve this problem, do as you wish. That was my absolute favorite part of this program. You have lots of freedom to express yourself and find creative solutions to complex problems.
Yeah, it's interesting to hear. Then you choose to make your master project in industry. Of course, you can also do it at the department, but you choose the industry. So why did you do that?
Yeah, so essentially, I have been feeling more catered towards the industry, working in a high tempo environment. It was also, a good way to actually get to use an actual quantum computer, which is one of the big drives for this specific project, right? But in general, I went to the industry because it's more. I feel it's more high tempo, more drive to go and do something in a short period of time. So yeah.
And perhaps that was also a good starting point to get a job in industry.
Yes, of course. I mean, I told you before I got the job from my internship, but I also got an offer from my supervisor to stay in the research department.
Okay, perhaps as a last question, I want to ask you a little bit about your thoughts about your future at Ericsson or elsewhere.
Yeah, I look very brightly at my future. Right now, I am very happy at Ericsson. I think as time goes on, I want to maybe move on a little bit more into development, coding a little bit more, I think. But Ericsson in particular is a nice company because you have all the opportunities to grow. You can very easily shift from one discipline to another within the company. I also think that as a physics student, I am like a knowledge sponge. So new challenges will very quickly absorb into my brain. So I feel like the world is open to me. I can go to the most places and adapt quickly.
Fantastic. That sounds like you have a bright future. So thank you very much, Marcus, and good luck in the future.
Our second program is in theoretical physics. It consists of a block of 5 mandatory courses listed here. In addition to the mandatory part of the program, there is a second block of recommended courses given here. Finally, it is to be complemented with elective courses to be selected among a wide spectrum of subjects. The graduation project goes from 30 to 60 credits, and it can be carried out in either an experimental or a theoretical research group. So to give you a taste of the theoretical projects, here is a sample of recent or ongoing master thesis projects which are connected to theory. So I will not read them all. You can see them written here. I would simply like to point out that some of these have led to research level journal publications. And you can see from the topics that there is a wide variety of cutting-edge research projects possible for a master's student. So we have been talking a lot about courses during this webinar. I'd like to be a little bit more concrete, and I would like to welcome Tom. So hi, Tom.
Hi, thank you very much.
So Tom, you recently took the machine learning for physicists course, which is a new course at university. Could you tell us a little bit why you chose this course and how does it connect to what you do here at the university?
All right. So yeah, first of all, I just have a general interest in machine learning. I find it very fascinating. But then as well, I am a PhD student here, and it relates a lot to my research within particle physics. But then as well, I just believe that machine learning is the future of society, both within science and outside. So it's very fascinating to learn about it. So that would be my reason.
Sounds good. So you mentioned actually you are a PhD student here at the department. So could you tell us a little bit more about the kind of the group of students that are taking this course?
Right. So yeah, I actually really like the mix because first of all, I am from Stockholm, I am from Sweden, but in the classroom there was a mix of, you know, both us from here and people from all over the world. So we had this very international feeling, which was a lot of fun to get to know people from everywhere. But then as well, we were a mix of PhD students and master students. So we had this kind of, you know, connection between science and students, which was a lot of fun. But yeah, but with that being said, I wouldn't say that the level was too high for a master student or too low for a PhD student. I think the level was good and the mix was, you know, a lot of fun. Yeah.
So a mix of master students and PhD students.
Yes.
So how is a course like this structured? Did you, for example, I'm curious, did you carry out any practical implementation of to any application?
Right. So Yes, we did. And yeah, so first of all, I would say that Jens, he's probably one of my favorite lecturers I've had. So he's the professor in the course. And so his main idea is kind of that, learning through doing. Of course, we had theoretical calculations and so on to learn all the concepts, the important algorithms and so on. But other than that, we had two main projects, and we had this huge variety of different projects we could work on. You were even able to come up with your own project, and some people went to science-related companies and so on. Me, myself, I did two projects. I did one working with Open Atlas data from the Large Hadron Collider, where I tried to classify and identify the Higgs particle. And other than that, I did regression. So I tried to predict formation of dark matter halos around galaxies. So it was very interesting to see how you could actually learn things, science-related questions using machine learning.
So it sounds like to me like you had some fun in the class, right?
Yeah, it was a lot of fun, to be honest. Yeah.
So Tom, thank you very much for your insight in this course, and see you around at the department.
Yeah, see you around, no problem.
Our third program is the Master Program in Physics. So the Master Program in Physics is subdivided into 4 tracks: atomic, molecular, and optical physics, particles and cosmos, quantum light and matter, and general physics. So concerning the track in atomic, molecular, and optical physics, here we focus on the study of interaction between light and matter at various scales from atomic to molecular level. We want to understand all these interactions and how we can use them to actually manipulate atoms, molecules in ways which were not possible even just a decade ago. The particles and cosmos track concentrates on the physics of the smallest constituents of the universe and its larger structures. We study elementary particles and their interaction, cosmology, the primordial universe, and its fundamental laws. The quantum light and matter track prepares the student to R&D work in areas of modern solid-state physics, quantum technology, and the study of fundamental quantum mechanics. It connects to a fast emerging and growing job market and a wide range of new industries. So I will now give the word to Supriya Krishnamurthy, who is researcher and lecturer at the master level in our department. And Supriya will introduce you to a few more teachers who are active in the programs.
I'd like to introduce you to 3 of the teachers you'll meet at the physics department at Stockholm University if you study here. They have all 3 of them received the very prestigious Teacher of the Year award from Stockholm University for their very great engagement, involvement, and talent in teaching. They are Emma Wikberg, Sören Holst, and Fawad Hassan. Emma received the Teacher of the Year award in 2018. Apart from the courses she teaches, she is also an educational developer here at the physics department and is very interested in all questions related to pedagogy. Sören received the Teacher of the Award just this year. He teaches general relativity in the master's program, and besides is also an author of several books and a very popular lecturer. Fawad received the Teacher of the Year Award 2015, and he teaches quantum field theory in the master's program, and besides is also very active in supervising PhD and master's students. Emma, could you elaborate a little on your role at the physics department?
Yeah, so I'm an educational developer here, which means that I'm involved in various projects that serve to improve the education from many perspectives, basically. And I also spend about half my time teaching. At the moment, I'm teaching mechanics and quantum mechanics at the bachelor level.
Great. And how would you describe the learning environment for students here at the physics department?
There are many things one could say, of course, but one is that we have a rather large research section and therefore many competent teachers in relation to the number of students. And also both teachers and research divisions are very welcoming. So for you as a student, it's easy to get to discuss physics with your teachers or to create contacts with the research groups. So typically, students do their master's projects as part of actual research projects at the department. The students often share rooms with PhD students in the group and so on. So it's a very open environment with a lot of contact between education and research.
Thank you. Fawad, can you tell us what your role is at the physics department?
Yes, so I do research and I engage in teaching. My research is in the area of theoretical physics, mainly in relation to the theory of gravity. In connection with research, I also have been working with very talented PhD students, and I also supervise master's thesis projects. So regarding teaching, I have been teaching a number of courses, but the main course I have been teaching is one on quantum field theory. And this is the formalism for describing the laws of physics at the most fundamental level, such as the standard model of particle physics, which, for example, contains the theory of photons, quarks, the Higgs particle, etc. But this formalism of quantum field theory is also used in condensed matter physics, for example, for understanding superconductivity. So that's what I do for research and teaching, basically.
Great. As a researcher, in your opinion, how does research affect teaching at the physics department?
Yeah. So in the department, we carry out frontline research in theoretical physics and experimental physics and in the overlapping areas. And we also benefit from the presence of Nordita, the Nordic Institute for Theoretical Physics, which is in the neighborhood. So first of all, these research activities affect the selection of courses that we offer at the master's level in the department. And these courses are taught by researchers themselves. And then along with the coursework, we also offer master's projects during which students work for up to 1 year on research level topics in close collaboration with active researchers, while often embedded in the respective research groups. So these projects can greatly help students in selecting their future research careers as PhD students, and also to teach them valuable analytical and computational skills that they can use in case that they want to move outside academia and they don't want to kind of pursue a research career in physics, for example.
Thank you. Sören, could you tell us a little bit about your role at the physics department?
Yes, so I'm mostly doing teaching, something that I enjoy very much. And I'm teaching both at the bachelor's level and at the master's level. And in the master's program, I'm currently teaching the course in general relativity.
I know you are mostly interested in theory, or maybe only interested in theory. Can you tell us why do you think it's important to do theoretical physics? After all, we know that physics is ultimately about explaining observations.
Yeah, of course. So actual observations is what all theoretical physicists try to base their theories on. And the reason why theory is important at a basic level, I think, has to do with consistency. So a theory obviously has to be consistent, that is free from contradictions. But this simple requirement has surprisingly far-reaching consequences. So historically, maybe the best example of this, or one very good example of this at least, I think is Einstein's special theory of relativity, which he developed essentially by insisting on a consistent treatment of then already known facts. And the theories that we are working with today, that is quantum mechanics, quantum field theory or general relativity, although they are all based on a fairly small number of basic principles or ideas, they turn out to be enormously complex and rich theories. In fact, the theoretical implications of these theories are not fully known today in all parts, or at least open to debate. And maybe even more interestingly, it is known that although these theories, of course, are consistent, internally consistent when taken separately, taken together, they are not consistent. You run into difficulties if you try to merge quantum mechanics and general relativity, for example. And this points to new physics beyond these well-established theories, only for theoretical reasons. And this I find very fascinating, how theory alone in this way can point us to new physics and help us come to grips with how the world works and its inner machinery.
Thank you, Sören.
So I really hope you found this webinar useful. And of course, you are welcome to contact us for more information. So here you can find the email addresses of the 3 program coordinators. In case you had any questions, please do not hesitate. You can also visit our website, www.physics.su.se. Applications and detailed documents that need to be provided for the applications to the program are provided at www.universityadmissions.se.